Everybody, it's Kavish again, and you might remember me from my previous sequences and series video, and this is basically a more specific, focused extension of that video. Today, we'll be going over one of the most popular math concepts ever. We'll be covering Fibonacci sequences. So, what is a Fibonacci sequence? Well, it's a recursive sequence that uses the sum of the previous two terms to find out the next term. This pattern starts from the third term because the first two terms are 1 and 1, and that's what allows the pattern to really be the pattern. So this is a recursive sequence and it's an infinitely repeating sequence, meaning there is no end to this sequence. So you might be thinking, what is the point of Fibonacci sequences? Well, they are just a simple sequence, but it's actually more than meets the eye. There's a lot of things that can be derived from Fibonacci sequences that I will cover later in the video. So in this video, I'll teach you what Fibonacci sequences are, and I'll give you two problems to solidify your concept of Fibonacci sequences. So let's go over what a Fibonacci sequence is first. So Fibonacci sequence, as you can see here, the pattern really starts from this third term and onwards. These first two terms are just there so that the pattern can work the way it works currently. It's what allows it to function. So the first two terms are 1 and 1. Those can't be derived from any addition of previous two terms or anything. They're just the first terms. So 1 and 1 add up to the next term in our sequence, 2. Then we use 2 and 1. We take the sum of that. We get our next term in the sequence, which is 3. 3 and 2. We take the next term of the sequence to get 5. And then you add them up and you get the next term in the sequence. This goes on forever. So let's go over a problem that uses what you could say is a problem solving method that you could use on problems that directly involve Fibonacci sequences, but this problem isn't really directly related to Fibonacci sequences. It is really helpful though, because it will help you tackle other problems that actually involve using the Fibonacci sequence, as you'll see in our second example. So this is from the 2013 AMC 10B and the 12B. This appeared in the same year for both tests. So this is a relatively hard problem, but we'll go over it together and break it down so that's really easy. So let's go over what the problem says. Two non-decreasing sequences of non-negative integers have different first terms. Each sequence has the property that each term, beginning with the third, is the sum of the previous two terms, and the seventh term of each sequence is n. What is the smallest possible value of n? So let's break this down. First here, we see two non-decreasing. We can't assume that's increasing because otherwise it would have had to explicitly say that. It could be just a sequence with the same numbers repeating over and over again. So, but for this case, we'll assume it's increasing so we can actually try and solve it quicker. Then we also see non-negative integers. Now here we definitely cannot imply it's only going to be positive integers because 0 might be involved, and I'm pretty sure it's going to be involved in this problem. The both sequences have different first terms, so that's really important to know because we cannot violate that rule or else we will for sure get the problem wrong. And each sequence has a property that each term beginning with the third is the sum of the previous two terms, kind of like the Fibonacci sequence. And the seventh term of each sequence is n, meaning that both sequences have the same seventh term. So let's start by defining each of these sequences. So let's say, we'll just say sequence 1 and sequence 2. Sequence 1 has two first terms, A and B. Well, not two first terms, so the first term would be A and the second term would be B. And for sequence 2, we'd have the first term would be C and the first term would be D. Because the pattern starts from the third, we can just define these as anything. So let's work out sequence 1 and then we'll get to sequence 2. So for sequence 1, we see that the first term is A, the second term is B. The third term would be the sum of these two, so it's A plus B. The fourth term would be A plus 2B. The fifth term would be 2A plus 3B. We can see that by just adding these terms. So it'd be 2A plus 3B. And then sixth term would be 3a plus 5b. And the seventh and final term that we're solving for would be 5a plus 8b. So this is the term we're trying to solve for, 5a plus 8b. So we know both sequences have the same seventh term, which is 5a plus 8b, or in this case, for sequence 2, it'd be 5c plus 8d. Now these two are equal to each other. So when we equate them, we can say that 5a plus 8b is equal to 5c plus 8d. Now we know that there's probably going to be a 0 in one of these sequences, and 0 can't be the second term. 0 has to be the first term, because if you have 0 as the second term, you clearly won't have increasing sequence. You'll have a decreasing sequence, but it clearly says non-decreasing here, so you'll have to have 0 as your first term. So when you have 0 as your first term, let's assume sequence 1's first term is 0. A is 0. So that's just saying that 8b is equal to 5c plus 8d. Now here, nowhere does it say that a sequence cannot have the same first two terms. It does not say that. It just says both sequences have to have different first terms. So sequence 2, let's assume for simplicity's sake that the first two terms are c for sequence 2. That simplifies things a lot more here. We can say that 8b is equal to 13c. This is because if both of these are c, you just add up the coefficients to get the thing. Now 8 and 13 here are relatively prime, so meaning we'll have to multiply them by each other to get the answer we want. So for that, we'll have to say that b is equal to 13, and let me just move this down a little, and c has to equal 8. Now to find the answer to this problem from this step, it's really simple. You just multiply 13 by 8 and you get an answer of 80 plus 24, 104, which is the answer to this problem right here. This is how we tackle the problem, by making it as simple as you can. But obviously on the actual MC, you want to check for other answers. Here, this is just the most simplest way, but it does involve some risks. There could be some more possible answers, but in this case, 104 is the correct answer to this question. So let's go over one more problem. This directly involves the use of Fibonacci, so let's go over it together. So Isaac has a steel tube that is 2024 units long. He wants to cut this tube into C smaller pieces such that no three pieces can be the size of a triangle with a positive area, and each piece has a unique positive integer length. Compute the greatest possible value of C. So we know here that there's a tube that is 2024 units long. He wants to cut it into pieces such that no three pieces, this is very important, can be the sides of a triangle with positive area. We can set a very simple inequality for this. We can say that a plus b, or the two previous terms, must be less than or equal to c. If this inequality is validated, then our problem can be solved, and it will be solved correctly, because if this inequality is validated, you can't make a triangle with these three sides. But we see here that a plus b can be equal to c. This is really important. So we can use the Fibonacci sequence here because the sum of the previous two terms is equal to the third term. So that's really important, and we can use that right now, right here, to solve this problem. So for that to happen, let's write down say the first 15 terms of the Fibonacci sequence. Obviously, during the test, you won't be doing this manually. You'd be doing this a much quicker way. But I'm trying to explain to you guys the thinking process here when you're trying to solve Fibonacci related problems. So we're going to have 1, 2, 3, 5, 8, 13, 21, 34. Then you're gonna have 55, 89, 144, 233, 377, 610, and 980. Let me just move this. 7. So let's just stop here. I think this is like around 15 numbers. I think that might be exactly 15 numbers. So right here is, let's say we'll stop and take a check. So the sum of all of these numbers right here is actually it's 2,582. So that is clearly over the 2024 mark, which we saw right here. So we see that there's 2,582. So we clearly cannot have this last number in here. We subtract this last number, and now instead of 2582 as our sum, we get 1595. So this is now 1595 units long. Now, when we subtract 2024 from 1595, we get 429 units. Now, we can't have 429 units as a block, because then this inequality would not hold true, and therefore our problem would not be solved correctly. So in order for that to happen, we have to remove this, and we can't have any more blocks. So this will be the total number of blocks we have of various lengths. Remember, none of these blocks can satisfy a triangle's sides. So let's calculate how many blocks we have. We have 14 here, so that means we have 14 pieces here. That means that 14 is the greatest value of C, and that is our answer for this question, because we cannot have the 15th term. Also, there are 15 terms here. You just ignore one of the ones. So there'll be 14 blocks here. So it'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And that's what your answer is, 14 for this problem. So this really gives you a good understanding of how to apply Fibonacci sequences. Fibonacci sequences, this is like a fun fact, just a little thing I want to add. If you guys have ever heard of the golden ratio, or like the spiral, like with all those squares, the Fibonacci sequence represents the golden ratio in sort of a way, because all of the numbers, I don't know the exact pattern, it's like every other number, something like that. When you find the value of that fraction, it is really close to it, to the golden ratio, which is like 1.618 or something. So like the Fibonacci sequence can be derived from the golden ratio, or vice versa. And the Fibonacci sequence applies to so many more things in different fields, like medical and business, and so many things use Fibonacci. So it's like really good to learn, and math competitions love to give you these problems. It's like it just throws you off, and if you know how to use these, it's really good, and it'll be a very powerful tactic to have up your sleeve. So that is it for this video. I hope you guys took away something from this lesson, and thank you for listening. And yeah, thank you.